So now we will continue with the next topic, that is about entropy for continuous variables. Hence, in case of continuous variables, we can plot their histogram or their normal distribution, or we can plot their KDE graph. So whenever we have continuous variables, their histogram is nothing but the values like V1, V2, V3, and so on, and their corresponding count. So we can say that V1 value is appearing suppose 5 times, V2 is appearing 3 times, V3 is appearing 7 times. So this will become the histogram. And there are no gaps between these bars. And if you want KD plot, then we simply connect the top of each of the bars. And this is the normal or probabilistic distribution as well. So if the distribution is having a high peak, if there is a high peak, it indicates that most of the values are concentrated in this particular range only. Most of the values are concentrated in this particular range. That means we can be definite that only this is the range of values. Only this one is the range of values. That means we have less confusion, more confidence. And if we have more knowledge, then we can say that entropy is less. On the contrary, if this is our region, that means the values are widespread. We are less confident of predictions in such a case, less accuracy, more confusion, less knowledge. That means more entropy. And our requirement is of lesser entropy. Okay. So whenever there is a high peak, that time we can say that entropy is less. Okay. Okay, so we have seen entropy for continuous variables and for the numeric, for the qualitative categorical values as well. So for categorical values, the entropy, the formula was minus P of I log of P of I, summation of all kinds of classes. Similarly, we can find out the entropy for continuous values as well by observation from the graph. Okay. Now, the use of entropy is just to understand about the splitting, that whether the split is pure or not. That means whether there is a necessity to split further or not. Okay. So this is the question that entropy answers regarding the splitting of the nodes in the decision tree. Now we need to study another concept called as information gain. Now, why is information gain important? Because it is used to train the decision tree and it measures the quality of the split, and it is used to understand that the sequence in which we are selecting the features for the nodes for splitting is appropriate or not. So if we have feature 1 over here, then we are considering feature 2, and then further feature 3, or first should we consider feature 2 and then feature 3. So the sequence of selecting features, this decision sequence, can be understood that which is the most efficient, such that we have lesser splits and more efficient decisions. This is understood by information gain. So it is about finding the attribute that returns the highest information gain. So we'll find out all such sequences, and on finding out all these sequences, wherever the information gain is maximum, the sequence for which information gain is maximum, we'll go with that particular sequence. And the formula to find information gain is in entropy of the parent minus weighted average of the children. So how this formula works, we'll see that. So again, if we consider this data set in which the person will play tennis or not, if we consider outlook as a feature, then we'll try for going for the entropy of the parent as outlook. So if we want outlook as the feature, we start with outlook. We need to find the entropy of the parent. Why? Because our main aim is to find information gain, which is entropy of parent minus weighted average of children into entropy of children. So firstly, we need entropy of parent. Suppose our parent or root or parent can be root of the entire decision tree, or parent can be a root of a subtree as well. So entropy of parent will be, we are considering all the features. So finding the entropy of the parent, in which we need to see the number of classes over here. So we have class like yes and no. So we need to find the probability of yes, probability of no, find out the logs, multiply, and find that entropy is 0.94. Now for the outlook has the values like sunny, overcast, or rainy. So we'll consider only that particular section of the data set in which the outlook comes as sunny. The outlook is sunny. Here the outlook is overcast. Here the outlook is rain. So rain only. So wherever it is sunny, we need to consider what is the label. We have already seen this in previous lectures. So we know that here we can see probability of yes is 2 times out of 5 and probability of no is 3 times out of 5. So we have substituted and we have calculated. Similarly, you have to do entropy for overcast and entropy for rain. So then we have found out the entropy of parent, that is outlook. For the parent, we have found the entropy. For each of the children, we have found the entropy, which is as shown on the screen. Now, weighted entropy of child means we need to multiply something with the entropy of each child. As you can see, these are the entropies of overcast, sunny, and this is sunny, and this is entropy of rain. So, what we are multiplying is number of examples over here. We have 5 labels or 5 examples over here. And here initially, how many labels we had or examples? We had considered all of this. We had considered all. Total, there are 14 examples. So the number of label examples for outlook is 14. For sunny, examples are 5. For overcast, we have 4 examples. And for rain, we again have 5 examples. So the weighted average for overcast is nothing but number of examples for overcast divided by number of examples for parent, that is outlook. Similarly, weighted average for this is also sunny. Then for overcast, so weighted average of overcast is number of examples 4 divided by parents examples 14. Similarly, weighted average for rain is number of examples 5 upon total is 14. So these are the respective weighted averages 5 divided by 14, which we have multiplied over here with their respective entropies. So this is called weighted entropy of children. Weighted average into entropy for each of the individuals. Take their summation, you'll get weighted average for the children. So whenever we have a parent and how many of our children, we need to calculate difference between parents' entropy and the weighted average of all children. So information gain for that particular subtree or that particular state of the decision tree will be entropy of parent minus whatever we have calculated, weighted average of children, which comes out to be 0.2. So information gain is nothing but change in entropy between parent to children. So it is called increase or decrease or in the entropy or the impurity that we can say whenever we do the splitting. Because we have the entropy of the entire parent, when we specify the children, its entropy gets distributed, we can consider, and hence we'll get it as 0.28 for that particular state of the decision tree. So in this way, what we do is we need to build individual trees. For example, we'll consider outlook as one feature. We'll do the splitting, which is dependent on the number of possible values for outlook, like rainy, sunny, overcast. Then we'll consider, suppose another feature that we had was humidity. What are the possible values? Normal and strong, suppose. We had another feature like temperature, which had the values like suppose low and high. And maybe another feature like wind, and we'll do it. So how many of our features are there? That means total number of columns. We'll do this. We'll take them as a candidate for the root node. Then we'll find out information gain over here, say IG1, information gain over here, say IG2, information gain over here, IG3. Then we'll find out which information gain is the maximum out of these three. Suppose IG1 information gain is maximum. Then we'll consider this as the splitting for the root. So now these particular options are eliminated and this one is selected. On selecting this, after doing the splitting, then what we'll see, after this branch, which feature should I consider next? That we will check. Suppose next feature that I want to consider is out of the remaining. Outlook is done. Now remaining is what? Maybe humidity, that I will consider for any branch. What are the possible values for humidity? Normal and strong. Now I will calculate entropy change, that is called as information gain, for humidity. Similarly, we have fixed this particular part. Okay, this particular part is now fixed. This part is fixed. Now, what is another possibility? We may have outlook with rain, sun, overcast. After rain, we will consider now temperature suppose. Okay, and then for the temperature may be high or low. Now we'll calculate in entropy change, that is information gain for this particular subtree. So now suppose we have IG1 in which we have considered humidity and IG2 in which we have considered temperature. If IG1 is greater, we will finalize this particular subtree and this will be our decision tree till now. So this will become our decision tree if IG1 is greater. If IG2 is greater, then this will become our decision tree. So in this way, we'll consider that for rain, which are the candidates, and then we'll finalize this one, suppose. Next, for sunny, which are the candidates? Again, temperature, humidity. If suppose humidity wins here, then we'll keep humidity. Okay, so in this way, for each branch we'll do. Okay, so let us revise this. Possible candidates, outlook, temperature, wind, humidity. We have outlook, overcast, sunny, rain, temperature low, high, wind, normal, and strong, and humidity again low and high. or whatever it may be, the values. Now for this, suppose this has got finalized. These have got rejected. Now what we will do? For outlook, possible remaining candidates or features are what? Temperature. We'll check for temperature. Possible values are what? We have low and high. Now, another possible candidate is for outlook. When we have home, it may be humidity, which may be low and high. Or for outlook, it may be overcast, in which we have temperature, normal, strong, whatever. Then we'll consider which is best for this overcast, which is the further best. We will select. So suppose this is better, then this we will finalize. Now in this particular tree, we have selected temperature, suppose. Now for sunny, which are the candidates remaining? Humidity and wind. So we'll check for humidity. Same, we'll also check for wind. Whichever is maximum, that will finalize. Then for rain, which is remaining, only wind, so wind will be finalized. So in this way, we can observe that number of possible candidates are reducing. So definitely we'll stop somewhere. Also, based on the pure split or impure split. Pure split is what? When all the labels are of yes type only and no type are 0. Or all the types are of no only, yes type is 0. When all the labels are of same type, that is a pure split. That time further we don't have to split. So stopping criteria means whenever all the features candidates get over, or whenever we have a pure split. So in this way, we can select that which is the better decision sequence using information gain, in which entropy is also helping us. Entropy helps us to understand whether the split is pure or not. So this information gain that we find out, it is done recursively, right? Because usually when we are operating on trees, even in data structures and algorithms, it is done recursively. Okay, so recursive greedy search algorithm. We are searching which is the best feature. Okay, so it is done at every level of the decision tree. This is level 0, level 1. Further, we will have level 2 and so on. So once the leaf node is reached when we have pure split. At pure splits, we have labels of only one type. That time entropy will be 0. So no more splitting is done. Okay. This is another example in which we are going to calculate the information gain, which is nothing but entropy of parent minus summation of weighted average entropies of all the children. This is just the representation of formula. Whatever we have done previously, no, that same thing is represented by this formula. It is calculated. So entropy, when we consider this particular sequence, suppose we have considered this feature. Suppose we have considered this particular setting by selecting feature 1 as the root. Then what will be the entropy of this sequence? Or what will be the entropy if we consider feature 2? That means we have done the root, we have taken root. For root, we have taken the candidate F1, feature 1. For root, we are taking the candidate F2, feature 2. And whichever gain is greater, suppose the gain, information gain is greater for feature 2 selection, then feature 2 is finalized as the root. So this is how using which feature should I start splitting first can be decided. So we have seen entropy, we have seen information gain, and then we have selected the remaining. Now, also, other than entropy, we have another particular feature, which is called as Gini impurity or Gini index or Gini coefficient. So if we want to consider Gini coefficient, now other than entropy, we have another thing called as Gini index or Gini impurity. So by default, whenever we use decision trees, this is definitely something which is predefined in the Python libraries. So whenever we import it from sklearn, by default, how this decision tree classifier works is, it will consider the splitting, whether it's pure or impure, based on Gini index or Gini impurity. This is because it is a little more efficient than entropy as an option. So by default, the purity check is not done by entropy, it is done by Gini. But this is a parameter, which is default parameter. By default, it is Gini. So if we want, we can change the value of this default parameter to entropy. Okay. Also, there are certain other parameters, as you can see, that maximum depth of the tree. These are certain hyperparameters based on which you can try to manipulate and get better accuracy, minimum splits, and so on. So the formula to find Gini index or Gini impurity is nothing but 1 minus summation of squares of all the probabilities. Now, suppose our label, we have features. So in our label, we may have yes, no, yes, no, no, and so on. We will have the examples. So we have only two types of categories or classes in the label. So what is the probability for whichever node we are calculating? No, suppose we are calculating the entropy of the parent, or maybe entropy of this child, or this child, or this child. Now, instead of entropy, we'll calculate Gini index of the parent, or Gini index of the child, and so on. So for this child, suppose we have 3 yes and 2 no. Okay. Total, we have 5 examples, 3 plus 2, 5. Out of that, probability of yes is what? 3 out of 5. Take it square. Plus, for no, it is 2 out of 5. Take it square. And Gini index will become 1 minus this value. This is how we calculate Gini index. Suppose entropy had to be calculated, then we know the formula, this one. Okay. So just replace entropy with Gini index from now on because of its efficiency. This is another way. So here are some examples in which Gini index has been calculated for particular nodes in which purchase is yes or no. So we have calculated. Also, information gain, which has been calculated as difference between entropy. Now on, you can calculate as difference between Gini index. So parents Gini index minus weighted average of child's Gini index. Okay. Instead of entropy, just use Gini index to calculate information change as well, information gain. Now, so here we are calculating Gini index as well as entropy to see how they differ or what is their minimum maximum value and so on. So if these are the two formulas for entropy and Gini index, and if for a particular node, we are getting probability of yes as the label as 1, means total probability is only of that of yes as the label, which is 1. That means for no, it is 0. In such a case, when all the labels are of same kind, of yes kind, then we know that entropy is 0. And if we calculate Gini index, that will be 1 minus py square, that is 1 square, pn square, that is 0 square. It will come out to be 1 minus 1, which is 0. So whenever all labels are of same kind, entropy as well as Gini index come out to be 0. So I'll write over here, same labels, then entropy and Gini index both are 0. This is our conclusion. Now, if we calculate it when we have equal probability for yes as well as no, means probability of yes is also 1 by 2 and that of no is also 1 by 2 for whichever node we are considering. In such a case, we know that entropy comes out to be 1. Let's calculate Gini index. It will become 1 minus half square plus half square, which is equal to 1 minus half square plus half square is 1 by 4 plus 1 by 4. It will become 1 minus half, it will become half, 0.5. So our conclusion is that when equal labels or equal number of labels, entropy will be 1, but Gini index will be half. This is another conclusion. Okay, so this is the comparison between Gini index and entropy. And in our plotting as well, we know that for entropy, this is our curve. And for Gini index, our entropy is 1. And for Gini index, our graph will be maximum up to 0.5. We have seen here, Gini index maximum is half, that is 0.5. So this is when the probability ranges from 0 to 1. So this is probability, and this is about entropy and about Gini index. Okay, I hope you understood this. So this is it for this lecture. Remaining will continue in the next lecture. In this particular lecture, we'll see how to handle when we have numerical features and categorical data. Now, as per our understanding till now, we know that if we have features and we have certain values over here, which are numerical, and we have categorical label, then how we need to split this, we know that we'll select one particular feature, and then based on, we'll select a particular value from here. Suppose we have a value like 5 over here, then we can say that whenever x1, that means whenever a value in the x1 feature is less than equal to 5, go in this branch, and whenever it is greater than 5, go in this branch. In this way, we are replacing these nodes from categories to a condition, like less than equal to or greater than. So this is how we were doing for features having numerical value. However, for doing this selection of value 5, that means less than equal to which value? There are so many values like 4, 6, 7 and all. Why did I select 5? How to select this value efficiently, or what is the process of selection, that we will see now. So as you can see, we have serial number and user rating, and we need the options like yes, no, for they're downloaded or not downloaded. So first step is that we need to understand that there are so many particular values. Since there are so many values over here, this may be 3.5, this may be 4.6, this may be 2.2. So we'll have so many values. In order to avoid this, we'll see the process. First of all, we need to sort the data on the basis of numerical column. So we can see this is sorted in ascending order. That is small to big. Second step will be split the entire data set or the data on the basis of every value of the particular feature that you have selected. Suppose we have selected user rating as the feature. Now here we have user rating as the feature. So we'll write user rating. What are its categories? let us say we select 1.6 as the user rating, then whichever rating is greater than, whichever is less than 1.6 will come on this side, whichever is greater than 1.6 will come this side, suppose. So instead of writing user rating and then its two categories, in this diagram what they have shown is, they have shown that write the condition only, and then whatever is on the left hand side is suppose yes, and whatever is the right hand side, that is suppose no. So in this way, there we can also represent the decision tree. Now we have taken the first row, that means user rating 1.6, and the remaining user ratings are in the no section, because in the no section, what does it mean? Okay, they have taken no this side and yes this side. Okay, so this side is no. So user rating greater than 1.6, no, this is the value. User rating greater than 1.6, yes. Right? So these are the values for greater than 1.6. Now what we'll do, we'll take the next point, that is 1.9. We'll split according to 1.9 now. So user rating greater than 1.9, this is no, and this is yes. If it is no, which two rows will come? These two. If it is no, all these values. Next, we'll take 2.9, 2.5, and so on. We'll go on. That means for each and every value of user rating, we'll do the splitting. With respect to that, lesser than that, greater than that. Or we can also say lesser than that and greater than equal to that. So after doing all the splitting, as you can see, the no section, that means the left-hand side, the left branch, the number of examples here is increasing and the number of yeses is decreasing. I mean, the number of times rating greater than 2.9 is reducing and the number of times rating greater than equal to 2.9 is increasing. So that will happen because we have sorted the data. That is why we can see this change in the number of examples on left and right branch. Now, in this way, we have split according to each and every value. So how to interpret this? Our feature user rating, a particular value in that greater than a particular value means this, we are calling it as D over here, and we are saying that our user rating greater than suppose V1, then user rating suppose greater than 2.9 or something, let us say it is V2, then user rating greater than 3.2, that is suppose V3. So user rating greater than each value of user rating, we are trying to see that. So we'll get left and right branch in all the cases as we have seen. So D is the data set. Okay, D is the data set. F is the column user rating, that is the feature. And V1, V2, V3 are the various rows of user rating column, or you can say various possible values of user rating. Now what we'll do is, we know that to select the efficient splitting, we need to find that which split is best. That means we need to understand which value out of the user rating we need to select. So in that, what we'll do, we'll calculate entropy of D. We'll calculate entropy of the parent and entropies of the children. So this is the condition, and these are the branches that are formed. So suppose these are children. So entropy of parent minus weighted average entropy of children, summation of that, we are going to find out information gain. We know how to find information gain. The formula is change in entropy or change in Gini index. Similarly, we find entropy change if we consider splitting with respect to the second value of the user rating column. Similarly, in information gain 3 and so on up to information gain n, where n is the length of user rating column. That means number of values in user rating column. And then, as you know, we find out the maximum gain that we are getting, max of all these gains. So for whichever gain is max, suppose IG3 is the max, then IG3 is for which split, or it is for the split in which we considered which user rating that we'll consider, which will be, suppose V3, then we'll consider splitting as per V3. Okay. So F is our root. What is the condition? With respect to V3, if it is greater, or with respect to V3, it is less than equal to. These are the two conditions. This is how we'll represent, or we can directly represent only one node like this, and either yes or no. So both these diagrams are equivalent. Okay. So do this recursively until you get all the leaf nodes. Means what? This selection that we have done for V3 is what? For the root. Now we have these nodes. Now these themselves will be roots for some subtrees. This is one subtree, this is one subtree, right? So we need to find the efficient splitting over here also. We have split it with respect to V3. Now, next by respect to which we have to split. So if we see over here, okay, so this is splitting with respect to 1.9, suppose. That means on the left-hand side, we are getting a subset of our data set. Okay, on the left-hand side, this is our subset of data set. On the right-hand side, this is our subset of data set. So we have distributed the data set to the left and right. Now, from among these rows only, we need to consider which value to select for further splitting. So either we'll say, now we will split according to user rating, suppose greater than 1.6 on the right side, less than 1.6 left side. Or instead of user rating, we may have another feature like suppose temperature or whatever the features. Then we can select for temperature also. Here apparently we have just one feature, so we are splitting with respect to that. Suppose we have, so we can split with the same feature also again. Here we are splitting according to user rating. Its child can also have splitting according to user rating. Okay. In our previous video, just make one correction. I had said that once we select a particular feature, we don't use it in the child. No, we can use it in the child. And here also there is one feature only. So just basis the pure splitting. If all the labels are of yes type, or all are of no type, or all are of the same type, that means we are getting a pure split. That time we stop. Okay. And we can select the user rating or whichever feature again and again in the children. The stopping criteria is only the user rating. Okay. That is only the pure splitting of the particular feature at the node. Okay. So recursively at each node, we have to apply this process in which we'll consider only these values now. On the right hand side, we can consider any of these values. Suppose we decide here. Now here we have to take decision. Then only the rows which have come here, we'll consider only them for splitting. Okay, I hope you understood. Now this thing looks quite expensive because if you have millions of rows, then what will happen? It is computationally expensive. But is this a right way of splitting? The answer is yes, because this is the only way that can be done. So mostly in training time will go because we need to decide which value we need to select for splitting. So selecting the efficient value takes lots of time because each value has to be tested individually and the tree has to be constructed. So in testing, it will not take much time because tree is already ready. We just need to apply the data. And as per the condition satisfaction at each node, we'll traverse up to the leaf node from the root and we'll get the answer that label should be yes or no. And the complexity is log n for traversals. That is searching actually. Now, let us see the case where